So notice at the top here we have alternative form of the equation of an ellipse. So notice we've seen something like this before. This is just a reminder that if you do have something in this form, it's not that kind of really nice standard form of an ellipse. That doesn't mean it's not an ellipse. If your A and your C are not the same number, so take a look at this example here, A and C are not the same number, but they do have the same sign. They're both positive. So that's telling us there's a very good chance that it is an ellipse. However, we would need to first write it in the standard form in order to be able to graph it. So we are going to need to, complete the square. So we're going to need to complete the square twice. I'm going to take my variables to one side, the same variables, I should say. So I'll do my x's first and then my y's, trying to get it in that standard form of an ellipse. Okay. And I'll take my constant and move it over to the other side. So that's what I'm going to start with, just to get myself into the completing the square mode. 36y. And then on the other side, we will have that -4. So I'm going to move the 4 over. So we need to complete the square twice, but you might notice that we have coefficients in front of our squared terms. And so in order to complete this square in the way that we need to, I'm going to factor out the greatest common factor from my x terms and my y terms. Now really, when I say greatest common factor, I really need to factor out the first coefficient. So hopefully these will come out nice for you, but that's the idea, is that I really need to get an x squared here, so whatever is that value is what I need to factor out. For us, we do get a fairly nice value there. And when I factor out the 9, which again, I need to take out whatever is the largest coefficient there, whatever the coefficient in front of the y squared is, I get this. And so notice what's kind of happening here. Okay, now we need to complete the square twice. So I'm going to think about what value I need to add for the x's. If we take half of or -2, we get -1. We square it, we get 1. So that'll be that perfect square. So I want to add that to the other side. Sorry about my spacing. Then I'm going to do the same thing with my y's. Half of -4 is -2, but squared is 4. So that's the value I need there. So it's going to look like that. And okay, now realize I didn't just add 1 to this. Because there's a 4 here, if we were to multiply this back out, what I did was actually add 4 to the left-hand side. So I'm going to add 4 to the right-hand side as well. Now when I think about the value that needs to complete the square for the y variables, if I take half of -4, I get -2. I square it, I get 4. But again, I didn't just add 4 to the left-hand side. Because of this 9, I want to think about the fact that I actually added 36. So I'm going to add 36 as well over here. Now I have kept my sides equal and balanced. Now I can rewrite this. So I have 4x minus 1 squared, and you're welcome to pause and do this yourself. Try to write it in that standard form. Then we have 9x minus 2 squared. And then on the right-hand side, we add, and you can see that we get 36. But we're still not quite done, because although it might be a little easier to see that this is the equation of an ellipse, we're not truly done until we have the right-hand side equaling 1. So now I will divide each piece, each term that I have by 36. As you can see, that will give us division by 9, and 4, and 1. So now we see that standard form of an ellipse. We have addition between our two squared pieces. We can see that the center, based on what we saw on the last slide, will be 1, comma 2. So that will be the center of the ellipse, 1, comma 2. And then we are using the fact that A is 3 and the fact that B is 2 to give us our vertical and horizontal vertices that we have from the center. So our x value, our A being 3 gives us the x direction. So I'll have 1, 2, 3, and 1, 2, 3. And our B giving us the y direction, 1, 2, 1, 2. And then we just connect the best that we can. And we will have our ellipse here. Okay, nope, all right. So do your ellipse, I'll do my ellipse. And we've got it done. A lot of completing the square happening there, as you can see. Okay, I'm gonna call that good. Now notice at the bottom here it says, what if that same thing that we had occurred, but instead of +4 we have +40, meaning that if we had brought it to the other side it would have been a -40 instead of a -4. Realize that if that had been the case, we would have ended up with the same thing. Just trust me on this, would have been exactly the same. The only difference would have been the constant on the right hand side. But the constant on the right hand side, if we were adding 40, if we had a -40 and then we added 40, would mean we actually have 0 over on the right hand side. So this is what we would get. I just realized that I have another x there instead of the y that I needed. Okay, there we are. And so what I want you to see is, since both of these things are being added, the only way to add two things together and have 0, if both of those things are positive, is to have both of those things be 0. And the only thing that can make this piece 0 is 1, and the only thing that can make this piece 0 is 2. So there is only one value that works, which means that this equation is actually a point. So if you remember from 11.3, that's the idea that's happening here, is there is always the chance, just depending on what your constant ends up being on the right-hand side, that you could have 0 instead of what you're hoping for, which is, an ellipse in this case. Okay, now something very similar with hyperbolas. Notice really all we're doing here, just like with the ellipse, is adding this idea of hk, which shifts the hyperbola to a different location on the coordinate plane. And so if we can just rewrite something so that we can find h and k, we can do those things that we've done already with hyperbolas in order to get the graph of it. So if you want, we need to complete the square again twice. So I have x squared minus 2x here. Then we will have the same thing with y, and I'm trying to give myself a little more space here. So just a little one, there we go. And then minus 4y squared minus 16y. I'm going to add something there, and then I'm going to bring that 19 over. So this is what I have so far. I am guessing on the hyperbola because although I have x squared, which is positive, I have a minus 4y squared. So the x squared is positive, the y squared is not positive, and so because of that, that's telling me hyperbola, since I do have both x squared and y squared. Now the left side is actually ready to have complete the square, but the x part, but the y part is not. So what I'm going to do is I'm going to factor out a -4 so that I just have y squared, because that's important. That's going to look like this, and we have our 19. Now we can complete our two squares. So for the first piece, we've actually already seen this. We would be adding 1. For the second one, we've actually already seen this, just the negative, so we'd be adding 4. Now, I am adding 1, but notice I actually have 4 minus 4 times a 4, so I'm technically subtracting 16. So it would look like this. Okay, hope you're still with me. All right, so now we have x minus 1 squared minus 4 times y plus 2 squared, and that equals 4, just from adding up the constants on the right-hand side. Now, if we divide each piece by 4, because we want to have a 1 over on the right-hand side, so everything gets divided by 4. Here we are. Notice that we actually will have kind of an interesting thing there. Y plus 2, when I divide that by 4, I just get y plus 2 squared. So I'll write it over 1 just so you can see, and then the right-hand side becomes 1. But this does tell us everything that we need to know. So when we look at this, we can see that we will have this center. So our A is, in this case, so notice our situation here. We have the first one, we have this situation right here. Okay. So our A is 2 and our B is 1. There we are. Okay. Our center is going to be 1, comma, negative 2. And so we can go ahead and put that on, 1, comma, negative 2. Okay. And then our asymptotes are coming from that A and that B. So y equals, you can go back all the way to the other page because it is the same in terms of the asymptotes, but we will have b over a times x, and then the negative of that too, negative 1/2 x. So with all that, with the fact, of course, that we have only x-intercepts here since x is positive. So I shouldn't say it like that, sorry. The x-intercepts are a little bit of a different idea now because of the fact that our center is no longer the origin. So what we're going to do is from the center that we have of the hyperbola, if I move 2 in the x direction on both sides, there you go, those are the values that we need. So instead of those being the x-intercepts, we now have this shift, but it's still the same idea because it's coming from the center. Then from that center as well, I do my 2 asymptotes. So make sure you note that this is from the center, That is important because I'm going to come from the center and I'm going to go up 1 over 2, down 1 over 2, and that creates 1 set of asymptotes, and then the same thing, up 1 over 2, down 1 over 2, my second asymptote here. And so hopefully it looks very similar to you, it's just, as you can see, slightly shifted, but we still go from the vertices. So now notice where our vertices are here, and we're going to come up and still approach those same asymptotes. So there's no difference there. So if you want, you can see in this case the vertices. We have -1, -2, and we have 3, -2. So I do want you to notice that that's coming from, notice the vertices have the same y value as the center, and that you're only shifting that A in the x direction from the center, from the 1 in the center. So 1 minus 2 is a -1, 1 plus 2 is 3, and that's what gives us our vertices. And that is section 11.4.